Hi everyone, welcome back. If you've been following this series, you know that we have been exploring many different conditions and medications, and today's presentation continues in that same vein. Today we're diving into the world of neurology, and we'll be exploring GABA, which is an important neurotransmitter, as well as Vigabatrin, which is an anticonvulsant medication. Let's talk about GABA first. GABA stands for gamma-aminobutyric acid, and it's an important amino acid neurotransmitter. GABA is formed out of glutamate, specifically when glutamate is joined by two glutamic acid decarboxylase enzymes that also bind with vitamin B6. What's interesting about GABA is that it is the main inhibitory neurotransmitter in the adult central nervous system. However, it is the main excitatory neurotransmitter in the pediatric brain. So this function does depend on age. GABA in adults is known for producing a calming effect and slowing brain and neuronal activity, which is important to its function in preventing seizures, which we'll be exploring a little bit later. It mainly acts through ligand-gated ion channels, which we'll also see later. And there are many disorders that are associated with GABA and improper GABA levels. First of all, these conditions are very neuropsychiatric and neurologic in nature, and they can include things like schizophrenia, major depressive disorder, autism spectrum disorder, generalized anxiety disorder, and low levels of GABA are associated with epilepsy and other convulsive conditions. How does GABA work in the body? GABA as we discussed, is an inhibitory neurotransmitter, and the mechanism of action is twofold in the body. And it has to do with GABA A and GABA B receptors. GABA A receptors are ligand-gated ion channel receptors. When GABA A receptors bind to GABA molecules, chloride flows into the intracellular space. This negative charge results in a lower membrane resting potential, yielding an inhibitory effect. GABA A receptors are mainly found in the limbic system and in the retina. This is in contrast with GABA B receptors. GABA B receptors are G-coupled protein receptors, and they bind to GABA to increase potassium that's pumped out of the cell, and it prevents calcium entry into the cell by activation of adenyl cyclase. The lack of calcium entry prevents this presynaptic release of other neurotransmitters, which is also an inhibitory effect. GABA B receptors are found in different places than GABA A receptors. Specifically, they are mainly found in the thalamus and the cerebral cortex in the brain. On the right-hand side of the screen, we have the GABA molecule. I do have a short 2-minute video that discusses the action of GABA in the body. Let's go ahead and we'll watch that together.
Welcome to 2-Minute Neuroscience. Explain neuroscience topics in 2 minutes or less.
As we talked about, GABA is an amino acid neurotransmitter. And you can see how, as we discussed, glutamate is converted into GABA. In the mature brain, it acts as an inhibitory neurotransmitter, and it makes the neuron less likely to fire action potentials. As we just talked about, there's GABA A receptors and GABA B receptors. So this ion channel opens and it acts on chloride. When the chloride ions flow into the cell, it makes it less likely that the action potential will occur because the membrane becomes hyperpolarized. So here we have GABA opening potassium channels, and the potassium flows out of the neuron. And again, it makes it less likely to fire action potentials. GABA transporters are important proteins that help determine the action of GABA in neuronal cells. Increased GABA can have sedative effects, and this is important because you don't want to mix GABA with things like alcohol or benzodiazepines that can increase this effect. Let's talk a little bit about Vigabatrin. Vigabatrin is the medication that we're focusing on today, and it's an analog of gamma-aminobutyric acid. It was first approved for use in the United Kingdom to treat seizures in 1989. However, in 1997, there were serious concerns raised with the safety profile of this medication due to visual changes in patients who were taking it. It was approved for use in the United States in 2009 to treat refractory partial complex seizures in patients over the age of 2. However, this medication is reserved for patients who have failed treatment with conventional anticonvulsive medications, and it requires routine visual monitoring to prevent visual changes and blindness. It works by increasing GABA levels in the brain. Specifically, it irreversibly inactivates the GABA transaminase enzyme, which leads to GABA degradation. This prevents GABA levels from decreasing by preventing GABA molecules from being metabolized into succinic semialdehydes. GABA arrests the excitatory processes and signals in the brain that can cause seizures. Here we have my references for this week's presentation, and I thank you very much for spending a few minutes of your time with me to explore GABA and Vigabatrin.